Good day all. Today the continuation of gravitation, that we are going to learn geostationary satellite, polar satellite and Kepler's law. Let us see in detail, children. Yes, children. Geostationary satellite. A satellite which revolves around the earth in its equatorial plane with the same angular speed and in the same direction as the earth which is rotated on its axis. We can call it as geostationary satellite. The height, we can say that height h, which is equal to t square r square g whole divided by 4 pi square whole power 1 by 3 minus r. Okay, the values we can write here. We know that t, which is equal to 24 hours, right? So that converted means 86400 seconds. So this is for the time period, and for the radius of the earth, r, which is equal to 6400 kilometer, as we know that, and g value you know that very well, 9.8 meter second power minus 2. Or we can convert into that kilometer, then we will get 0.0098 kilometer second power minus 2. Then here we need to know this r value, everything. Yes, here we can apply, right? Applied the value, then we will write 86400 whole square into r square, that is 6400 whole square into 0.0098 whole divided by 4 pi square, okay, power 1 by 3 minus 6400. After, if you simplified this, you will get the value of, for this part, 42330 minus 6400. Okay, so the height from this, if you have calculated, then you will get 35930 kilometer. So this is the height of the satellite, geostationary satellite from the earth. Yes, children, now we'll see condition for the geostationary satellite and the uses of geostationary satellite. The condition, which is it should revolve in an orbit that is concentric and the coplanar with the equatorial plane, and we can say its period of revolution, which is around the earth, should be exactly same as the earth of about its own axis, right? And we can say that it should be revolve at a height of nearly, that is 36,000 kilometer above the earth's surface. So uses of geostationary satellite, let us see that. It is actually in the communication world, we can say it is communicating radio, TV and the television signals which across the world. So the geostationary satellites acts as a reflector such signals, okay, and it's studying the upper region of the atmosphere, and also it helps for the forecasting, weather forecasting, and determining the exact shape and the determination of earth, we can say, and it helps for solar radiations, cosmic rays, and studying the meteorologies, all those things. The geostationary satellite is used. Yes, students, now we'll see polar satellite and the uses of polar satellites. See, polar satellites, this is a satellite which revolves in a polar orbit that is perpendicular to the equatorial plane of the earth. So this is more closer than the comparatively with the geostationary satellite. And as we said, it is a low altitude. It's such the satellite will complete one trip around the North Pole to South Pole, about 100 minutes, make about 14 revolutions per day. So because of its low altitude, the satellite can view only a small strip of the earth in one revolution, right? So as the earth rotates about its axis, as we know that is east to west, okay, east to west revolution. So this is also east-west direction. So the satellite, it is in the successive revolution views in the whole day. That is a step by step during the entire day it will do. So the polar satellites, we can view the polar and the equatorial regions close distance, right? See the uses of the polar satellites. The uses, we can say the polar satellites actually are used in weather environmental monitoring. So they provide more reliable information than the geostationary satellite, because this is more closer than the geostationary satellite. Now they are used for the spy work, like military and all. It is used as a spy work, and we can say that the British polar satellites only the first detected the hole in ozone layer. And also we can say about the polar satellites are used to study the topography of Moon, Venus and Mars, right? Now let us see Kepler's law of planetary motion. It has three laws, right? Law of orbits, law of areas and law of time period. So one by one let us see. That is law of orbits. First law, the statement which says each planet revolves around the sun in an elliptical orbit with the sun which is situated at one of the two foci. It has S and S dash, that are the two foci we have taken, right? As you are seeing on the diagram, that planets which moves around the sun in an elliptical orbit, right? And ellipse has two foci, that is only I said S and S dash, right? Now the sun which is remains at one focus, that is S. Now the point P and A are on the orbit, which are called perihelion and aphelion. So perihelion and aphelion which is there, and it is represented the closest and furthest of the distances from the sun. So this we can say that for the law of orbits. Now law of areas, which is for the second law, the statement, see the statement, the radius vector drawn from the sun to a planet sweeps out equal areas in equal intervals of time period. So that is, see the diagram. So we can say the statement as the aerial velocity of a planet around the sun is constant. So suppose a planet which takes same time to go from position A to B. See the diagram children, as it is going from C to D, right? So from Kepler's second law of motion, the areas A as B and C as D, that must be equal children. Clearly that you must know. The planet covers the largest distance CD when it is near the sun than AB. So when it is further away, the same intervals of time. So hence the linear velocity of the planet is more when it is close to the sun than its linear velocity when away from it. So that only the aerial velocity of the planet around the sun is constant. Now the laws of periods, that is third law. The square of the period of revolution of a planet which around the sun, which is proportional to the cube of the semi-major axis of its elliptical orbit. If suppose we have taken capital T is the period of revolution of a planet and A is the length of the semi-major axis of its elliptical orbit, then we can say as from the statement T square, which is directly proportional to A cube. So we can write T1 square by T2 square, which is equal to A1 cube by A2 cube. So that the larger the distance of a planet from the sun, the larger will be the period of revolution around the sun. Yes students, so far we have learnt about geostationary satellite and uses of geostationary satellites, what is polar satellites and its uses, necessary condition how it should be, the polar as well as the geostationary satellite, Kepler's law of motion, all the three laws we have studied elaborately. Hope you people will understood. Thank you students.